Next topic we're going to look at is correlation and regression, starting with the first topic, correlation. And we're going to look at drawing a scatter plot and calculating correlation coefficient R and test the hypothesis with H0, and the parameter is given by a Greek letter rho. All right, again, quick review of previous chapter when we dealt with inferences about two samples. One of them was proportion. In the case of a proportion, we calculate the p bar, x1 plus x2 divided by n1 plus n2. And the test statistic is based on that, p1 hat minus p2 hat over the square root of p bar q bar over n1 plus p bar q bar over n sub 2. And we do the test of hypothesis, we do the confidence interval with that. In the case of a p-value method and critical value method, they're always equivalent regardless. When it comes to proportion, they may not be, because as you can see, the formula uses p bar for test statistic. But for the estimate E, it doesn't. It uses P1 hat, Q1 hat. Take a look at the sigma of P1 hat minus P2 hat, everybody. So with that being the case, E is Z alpha over 2 square root of P1 hat, Q1 hat over N1 plus P2 hat, Q2 hat over N sub 2. And this is slightly different than what we use over there. So I wanted everybody to see that. And so with that being the case, because over the course of past couple of sections, maybe we had that wrong formula. In the case of two means, three things happen. The sigmas are given, the population sigma 1 and sigma 2. We use the z-score. They are unknown, we use the t-score. If we assume sigma 1 and sigma 2 are different, we use a test statistic with S1 and S2, and we do the math. If we assume they are equal, we use S sub p, which is a weighted one, a pooled sample variance. As you can see, the formulas are different. However, generally speaking, we use the second case where test statistic t is x1 bar minus x2 bar over the square root of s1 squared over n1 plus s2 squared over n sub 2. I'm repeating this because it's worth hearing it, because we don't want to make a mistake. The last case for the means would be when we are dealing with two dependent samples. In essence, it becomes one. And the most important thing to remember is this very last sentence. When the values are dependent, do a t-test on the difference, which means you treat the difference as one sample and you do the t-distribution on that. It's t-distribution and the t. You just look at the differences and you go to previous chapter and you follow that. That's how easy it is. But as far as terminology, this means the individual differences, if you will. And then we have the mu of d. That means the mean value for the difference says d. We have d bar, the mean value for all the d's. S sub t, standard deviation for those values, and n is the number of pairs. If you have two variances, we just looked at it, the most important thing is know that the table is limited. The test statistic is S1 squared over S2 squared. And what we do is we try to choose the one with the larger variance as the first group such that F becomes larger than 1. And therefore you use strictly a right tail test. So even if it's a two tail test, you cut it in two and you go to a table with the proper alpha. Remember, table is limited, alpha is 0.05, that's one table. Alpha is 0.025, alpha is 0.01, you name it. And so there are 2 degrees of freedom of the numerator, n1 minus 1, and the denominator, n2 minus 1. Now we are looking at correlation. The key concept is, in addition to hypothesis testing and confidence interval, inferential statistic determines if a relationship between two or more quantitative variables exists.
A correlation exists between two variables when the values of one variable are somehow associated with the values of the other variable. A linear correlation exists between two variables when there is a correlation and the plotted points look like a straight line.
This section considers only linear relationships, which means that when graphed in a scatter plot, the points approximate a straight line pattern and methods of conducting a formal hypothesis test that can be used to decide whether there is a linear correlation between all population values for the two variables. The linear correlation coefficient R is a number that measures how well paired sample data fit a straight line pattern when graphed, measures the strength of the linear association between the two variables. Use the sample of paired data, sometimes called bivariate data, to find the value of R, and then use R to decide whether there is a linear correlation between the two variables.
Regression is a statistical method used to describe the nature of the relationship between variables. That is, positive or negative, linear or nonlinear. Questions. Are two or more variables related? If so, what is the strength of the relationship? What type of relationship exists? And what kind of predictions can be made from the relationship?
The synopsis of the section is that correlation deals with the relationship. Are they related? By the way, when we establish that, it doesn't mean if there is a causal effect. There is no cause. We are just establishing a relation. It's bivariate. We're dealing with two variables, x and y. And if there is a relationship, what is the strength? And the relationship may be linear or nonlinear. We are interested in a linear relationship as far as this one is concerned, okay? A linear correlation. And if it's so, can we use prediction? Meaning, is there a way to come up with something that can predict what's happening in the future, which means you come up with an equation of a line known as a regression line, which is the best line of fit, and you can predict what comes up. So that's the idea behind regression and how we put all of this together. So as far as a scatter plot is concerned, and you can see it on the right side, basically you plot points. That's all you do. X is the independent variable. Y is the dependent variable. And I hope everybody remembers when we were dealing with algebra, slope-intercept form was y equals mx plus b, where m was the slope and b was the y-intercept. And so if m is positive, you have the first type. Take a look at the top one. If it's negative, you have the second one. And the other two, the third one doesn't have anything as far as correlation, doesn't show anything. And the last one, it is nonlinear, and some of you may realize it's quadratic.
Distinct straight line or linear pattern, we say that there is a positive linear correlation between x and y, since as the x values increase, the corresponding y values also increase.
Distinct straight line or linear pattern, we say that there is a negative linear correlation between x and y, since as the x values increase, the corresponding y values decrease.
No distinct pattern would suggest that there is no correlation between x and y.
Finally,
Distinct pattern suggesting a correlation between x and y, but the pattern is not that of a straight line.
part A, basically x gets larger, y gets larger. Part B, x gets larger, y gets smaller. Those are the two that we are interested in. If we come up with a scatter plot that looks like part C, there is nothing we can say. Now, when is large? So if you go back to the numbers at the bottom, it gives you R, which is the correlation coefficient. This is fairly large. So is this one in an absolute value. So R represents the strength of the correlation, and it's between -1 and 1. And that's important to understand. If it's close to 1, it's strong. If it's close to -1, it's strong. And if you look at part C, there is no correlation. And as I mentioned in part D, there is no linear correlation, but you may see a quadratic relationship. There is a relationship. Are two or more variables related? If so, what is the strength of the relationship? To answer these two questions, statisticians use the correlation coefficient, a numerical measure to determine whether two or more variables are related and to determine the strength of the relationship between or among the variables. Linear correlation, R, the linear correlation coefficient R, measures the strength of the linear correlation between the paired quantitative x values and y values in a sample. It determines whether there is a linear correlation between two variables.
There are two types of relationships, simple and multiple. In a simple relationship, there are two variables, an independent variable, predictor variable, and a dependent variable, response variable. In a multiple relationship, there are two or more independent variables that are used to predict one dependent variable.
There may be more than one independent variable. Remember, in the case of y equals mx plus b, y depends on x. By the way, sometimes you can interchange it. What happens when we have more variables? That also can be discussed. But in this case, we're interested in one variable for independence. So with that being the case, let's finish off number 4.
Predictions are made daily in all areas. Examples, weather forecasting, stock market analysis, stock market analyses, sales predictions, crop predictions, gasoline price predictions, and sports predictions. Some predictions are more accurate than others due to the strength of the relationship. That is, the stronger the relationship is between variables, the more accurate the prediction is.
So the point is, this is a very important branch of statistics, and it works better in some cases than others. Okay, depends on the strength between the variables or among the variables. In many cases, by the way, you have a lot of variables to consider, but the concept comes from this idea of correlation. Let's look at a very simple example. We are given the table and we want to construct a scatter plot for the data shown for car rental companies in the United States for a recent year. We have different companies, A, B, C, D, E, F, bunch of companies, and the cars in 10,000s, and then the revenue in billions. So company A, for example, we see two numbers in front of it, 63 and 7.0. That means 63 times 10,000 or 630,000 and $7 billion in revenue. Just as an example, company B, 29.0, that means 29 times 10,000, 290,000 cars, and then revenue is 3.9, that means $3.9 billion. Obviously, the rest follows, so that shouldn't be a big deal at all. You want to come up with a scatter plot. In short, it means that you have the x and y axis. Okay, so look at this. This is the pair. This is one pair. So we want to draw and label the x and y axis and plot each point on the graph. So for example, the second pair would be 29, 3.9, and the rest of it. So we have 1, 2, 3, 4, 5, 6 pairs, and we're going to plot the points. I don't think anybody has any problem in points. You just got to be fairly careful, especially when you have a small size data, and plot accordingly. So just for the sake of argument, if we call this the very first pair, this would be the one. You see that, everybody? First pair. Okay, 63, 7. So the x-axis cars in 10,000s, the y-axis the revenue in billions of dollars. Okay, so I hope it is clear to everybody. Just as an example, if this is pair number 2, okay, this is pair number 2. Okay, 29, 3.9. We can easily see the pair, and we have an idea how we come up with the rest. I want to quickly go over technology if you want to use that, but this is very simple and straightforward. So to do that, First, you clear the list, you put the data into L1 and L2. So start, edit, clear list L1 and anything else, L2. And you put it, you just input the data. Then, you're going to press on Y and clear, and second Y scatter plot, enter on, enter, select X1, list as L1, and so on and so forth. This is very straightforward. This is the detailed one. It shows you what to do. Okay, so take a look at what happens here. Now, the last one, mark, is what you put in. You want it to be dots or plus, whatever that you decide. It's just a mark showing what comes up. If you do the drawing, whatever you choose, it shows up here. So this is your scatter plot. Obviously, for a simple case such as this one, you can just do it by hand. It's really not that big of a deal. I believe everybody can do that. So again, first input L1 and L2, and then go to the scatter plot and enter that. This is how we construct a scatter plot. The correlation coefficient computed from the sample data measures the strength and direction of a linear relationship in two variables. There are several types of correlation coefficients. The one explained in this section is called the Pearson product moment correlation coefficient, or PPMC. And so Pearson product moment correlation, or simply a correlation. And we use rho to represent that for the population. Now, as you can see, the strength here, it shows the strength. If it's close to 1, is strong. How close is close? You really have to do the test of hypothesis to make a decision. But normally 0.7 and higher is good, negative 0.7 and less is good.
The correlation coefficient computed from the sample data measures the strength and direction of a linear relationship between two variables. There are several types of correlation coefficients. The one explained in this section is called the Pearson product moment correlation coefficient. The symbol for the sample correlation coefficient is R. The symbol for the population correlation coefficient is P. The range of the correlation coefficient is from -1 to +1. Sorry.
That's fine.
If there is a strong positive relationship between the variables, the value of R will be close to +1, 0.7 or larger. If there is a strong negative linear relationship between the variables, the value of R will be close to -1, -0.7 or smaller.
We use R for sample correlation, and for population, we use rho. These are just symbols. N is the number of pairs, summation of x is summation of all x's, summation of x squared is sum of x values that are squared, summation of x quantities to the square, that means add them up, and then, and we want to definitely avoid confusing these two, because I've seen that sometimes students don't distinguish between the two, okay? We've been through that when we did the standard deviation, so we should be fine. Summation of xy indicates that each x value should first be multiplied by its corresponding y value, and then add them up, basically. R is the linear correlation coefficient for sample data. Rho is a linear correlation coefficient for a population of paired data. So, given any collection of sample paired quantitative data, that's the key, quantitative. It has to be quantitative, so we can come up with the linear correlation coefficient R. So the linear correlation coefficient R can always be computed, but the following requirements should be satisfied when using the sample paired data to make a conclusion about linear correlation in the corresponding population of the paired data. So with that being the case,
The sample of paired XY data is a simple random sample of quantitative data. Visual examination of the scatter plot must confirm that the points approximate a straight line pattern. Because results can be strongly affected by the presence of outliers, any outliers must be removed if they are known to be errors. The effects of any other outliers should be considered by calculating R with and without the outliers included. In other words, requirements 2 and 3 are simplified attempts at checking that the pairs of XY data have a bivariate normal distribution.
Outliers can create a problem. That's why we want to be careful of those for a simple reason. When we do the correlation and we do the test of hypothesis on that, ultimately the idea is that to come up with a regression line that works. And the regression line is extremely affected by outliers. That's why we want to check for that. And I'll explain that as we come across examples of that. All right, as you can see, R is very complicated. And needless to say, you have access to it as far as the formula is concerned. You can use the formula sheet to use that, and we can use technology to evaluate it. So you are exposed to both of them. But R is n summation of xy minus summation of x times summation of y over the square root of n summation of x squared minus summation of x quantity squared times n summation of y squared minus summation of y quantity squared. Very complicated, but no worries. You have that. Now, there is another way of saying the same thing. Z sub x denotes the z-score for an individual sample value x. Z sub y denotes the z-score for the corresponding sample value y. R is summation of z sub x, z sub y over n minus 1. The difference is this is easier to grasp and understand. How do you come up with z sub x? You look at just the x values and you calculate the z-score for each one, which is z equals x minus mu over c. We'll go over that just for the sake of argument to see how it's done. So there are two ways to calculate it. The second method, it's easier to understand the concept. All right. So let's look at an example and see how this thing goes. So here's a table. The table lists 5 paired data values using technology to find the value of the correlation coefficient R for the data. The idea is that normally we use technology. So if we look at what's given in technology, take a look at what is boxed in red. That is the value of R. So if you're using technology, so from the technology, StatDisk, Minitab, StatCrunch, Excel, StatTI, the value of R will be automatically calculated, and all of them give you something like 0.795 and show you how it's done by hand. So given that, and that's the formula. So I want to show you that it's really not that bad when you have just a few pieces of data and you want to calculate. Look at the formula. According to the formula, we need to calculate summation of x, summation of y, summation of x squared, summation of y squared, summation of xy. So let's come up with this table. First, x and y we write it. Then we add x squared column. 5 squared becomes 25. 6 squared becomes, this is this table squared. So this one squared, and you get to that. Square these numbers, and you get these numbers. Multiply these two numbers, and you get this. Multiply these two numbers, and you get this. The process may be long and tedious, but the concept is extremely simple to understand. So what do we do now? We add one more row at the bottom. We add all those in the column. So the x column, we add them up. The y column, we add them up, so on and so forth. So when we add them, those are the numbers. Now look at the top formula in blue. You have everything. N being number 5, just plug in. 5 times summation of xy is 159 minus summation of x is 24 times summation of y is 31 over the square root of n summation of x squared is 118 minus summation of x is 24 squared. We close the brackets, and the new brackets, n is 5 times summation of y squared, which is 251, minus summation of y, which is 31 squared. Do the math, you come up with the answer, 0.795. So can it be done by hand? Well, when we have only 5 pieces of data, it's manageable. Do you have to do it by hand? No, but you should know how it's done because of the formula. Now, what if we wanted to do it with TI? We put the information in L1 and L2, and TI calculator, linear regression test will give you the value of R. You have to do that. It gives you more than that, but you have to do that. So you use that stat test, linear regression t-test, enter L1 and L2, if you want to choose whatever, in this case not equal. Take a look at what happens when you put that. So X1 list is L1, Y1 list. It is normally that. As long as you put L1 and L2, as long as you do this part, when you want to go to the linear regression t-test, it is L1 and L2. Basically, you have to just enter, and all the way to calculate. Really, you don't have to put in much because normally, unless you don't put the information, the data into L1 and L2. And here's the result. So what I want you to pay attention to, because of the arrow here, I'm showing you the second part. Okay. Now, it gives you the test of hypothesis for the correlation coefficient with the p-value. It gives you A and B, y equals A plus BX. This is the regression line with A being negative 11 and B negative 11.2857, so forth. And B is 3.6428, so forth. So what is it that we need? We are interested in this one, and we have no choice but to go through the process to find it. So if you want to go with the technology, you have to go this far. So for this question, I want to show you the second formula that was discussed, again by hand, but mostly things will be done with technology. What I want to do, I want to use this formula, z sub x, z sub y over n minus 1. Okay? Now, this formula has the advantage of making it easier to understand how R works. The variable x is used for the chocolate values, and the variable y is used for the noble values. Each sample value is replaced by its corresponding z-score, z sub x and z sub y. I will show you how to calculate just one of them, and then you'll see how the rest goes. And again, that will take some time. Okay. So z sub x is calculated, z sub y is calculated. You multiply. So these two columns are being multiplied. So the first one would be 0.239046 times negative 0.052164, giving you negative 0.012470. As an example, this times that equals this. Okay. And now this very last column, add them up. Okay, that's the summation. Add them up. That is your numerator class. So the z-score for all the chocolate values, see the third column. The z-score for the noble values, the fourth column. And the last column lists the product. Okay, everybody? Put it into the formula. N is 5, so 5 minus 1. And you get to the same answer. Now, how do we calculate z sub x? I want to show you, I want to remind you. Okay? You need to look at the x's, and for this data, you have to find x bar. That means you add them up and divide by 6. And you have to find s. Okay? It's the summation of x minus x bar quantity squared over n minus 1. And it has to be the square root of that. And then z is x minus x bar over s. This is the square root, everybody. Okay. So that's, everybody remembers how we calculate the z-score. The z is what? X minus mu over sigma, or x minus x bar over s. So that's how you calculate it. So for example, for the very first entry, okay, number 5, okay, x is 5, x bar is calculated as 4.8, 5 minus 4.8, and divided by s, which is 0.83666, and it gives you 0.23905. So I hope you see that this number is this number, everybody. So if you can calculate one, you can calculate all. Does it take long? Yes, it does take some time.